In the preceding video, we discussed the production process of a typical thin film amorphous silicon solar cell on lab scale. We will now discuss the thin film module manufacturing process on an industrial scale. The module manufactured on industrial scale have the same basic structure as the lab scale solar cells. The cells are deposited on top of the glass substrates using the same deposition techniques. However, the glass substrates can have a size of over 5 square meters, which makes deposition of homogeneous layers a serious engineering challenge. The biggest difference between the cells and the modules, however, is that module manufacturing requires multiple cells to be interconnected. The series connection of the cells is achieved through laser scribing. As explained in the video on laser scribing, the first scribe is performed after the TCO deposition. 2 more scribes follow after deposition of the photoactive layers and the back contact. Let's take a look at the automated production line of Sunfab, an American company that made thin film silicon modules on glass substrates. The process starts with the front loader robot lifting 5.7 square meter glass substrates onto the conveyor. These glass substrates already have a front TCO layer. The process is fully automated, so the conveyor moves the substrates from one deposition area to the next. The edges of the glass are rounded to prevent them from chipping, after which the substrates are cleaned. The glass then enters a laser scribe where the P1 scribes of the front TCO layer are performed. We are now ready for the deposition of the silicon layers. The conveyor moves the substrate to the plasma-enhanced chemical vapor deposition chamber where the P-doped layer is deposited first. Several of these large PECVD systems are used, and in each a different type of layer, either P-doped, intrinsic or N-doped, is deposited. This is the glow discharge of the plasma in one of the chambers. These large PECVD systems are actually developed by adapting tools from the flat panel display industry. After the silicon depositions, the second laser scribe, P2, is performed before moving on to the sputtering deposition of the back contact. After sputtering, the final laser scribe is performed. Now we have a PV module that is capable of generating electricity. Then the so-called shunt removal system further isolates the sides of the substrate to prevent shunt leakages. Since 5.7 square meters modules are not always so convenient, the modules can be cut into half or quarter size depending on the customer's requirements. Next, the photoactive film on the edges of the module is removed for greater reliability. The film on the edge might limit the current output of the module due to the imperfections in the production process and are therefore removed. Now, bus bars are added. The glass is now ready for lamination. A foil is cut in the right size and placed on glass, followed by a sheet of back glass. The laminator spreads the foil out evenly between the front and back glass, thereby encapsulating the device. This makes it wind and water resistant. The module is then subjected to a high pressure, high temperature annealing process to remove trapped gases and create a good contact between the individual layers. Finally, a junction box is connected to the module with standardized connectors to facilitate installation. The performance of the module is then tested by a solar simulator to see if the module meets the specific output requirements. The yield of such a production line is generally over 95%, meaning that under 5% does not meet the specified requirements and is discarded. We now have a finished PV module. This is a most common thin film production process. The 2 big equipment manufacturers that have developed a fab for thin film silicon modules on glass were Applied Materials and Tokyo Electron. However, as we discussed, one of the advantages of thin film solar cells is that they can be produced on flexible substrates. One company that produces such flexible thin film silicon solar cells is Hyatt Solar, located right here in the Netherlands. Rather than the batch processing we just saw in the video, Hyatt employs an innovative roll-to-roll production line where aluminium foil is transported through the different processing chamber. The first step involves the deposition of the fluorine-doped tin oxide TCO layer onto the aluminium substrate. This is done during atmospheric pressure chemical vapor deposition at a temperature of about 500 to 550 degrees Celsius. Then, the silicon layers are deposited using plasma-enhanced chemical vapor deposition. With this process, Hyatt produces both single-junction amorphous silicon cells as well as micromorph tandem cells. The silicon deposition is followed by the sputtering deposition of the back contact. For the sharp observers among us, indeed, no separate laser scribing step have yet been performed. The monolithic series integration of the module is realized during a unique single patterning step by means of a laser scribing and printing. Following the series integration, a conducting carrier foil is deposited on top of the back contact. After lamination of this permanent carrier foil, the aluminium foil is etched away. The aluminium is just a temporary carrier that is required to withstand the temperatures of the atmospheric pressure CVD and PE-CVD process. Then the foil on the roll, which can in principle be up to kilometers long, is cut to the required size and contact wires are added. During the final step of the process, the module is encapsulated. The weight and fragility of the current dominant PV technologies based on glass modules rule out many applications like surfaces on lightweight and curved facade and roof constructions. In these pictures, the advantage of lightweight modules is demonstrated. They can easily be integrated in semi-finished facade and roof elements with complex three-dimensional geometries. There is a clear market for the unique selling point of flexible lightweight modules. The effective use, due to very simple and cheap custom sizing of the modules, allows a much better use of the available area and compensates in many cases easily the lower efficiency and allows similar system powers on the same available area as with glass-based systems. In summary, in this section we discussed the typical structure of thin film amorphous silicon solar cell, and we looked at the techniques and processes involved in fabricating such a solar cell on lab scale. We then looked at the production process of thin film silicon modules on glass substrates on an industrial scale. Finally, we discussed the innovative Hyatt Solar process employed to fabricate flexible modules. In the next and final video of the thin film silicon section, we will discuss the best performing thin film silicon solar cells today.